Okie doke. All right. So, yeah, let me throw this in Brady Bunch view here so we can see everybody who's got their things on. This is the last of the weekly sessions. So what I wanted to do is just kind of open it up and say that any questions about any chapters or any concepts, it's kind of the last opportunity until we get together face to face. And I just want to double check the dates. The 28th and 29th, right? Next Wednesday and Thursday. Everybody clear on that? Wednesday and Thursday, the 28th and 29th, we'll be getting together there at the college, Eastern West Virginia. Do you guys, pretty much everyone on the call, not everybody, but you guys know the building, know how to get there, all of that?
Yeah.
Okay, yeah,
As long as Mason does, I'll get there.
yeah, Mason will get you there. And we'll be meeting up on the second floor. I forget the room number, but it's not that big of a building. You just go up the steps or up the elevator and you're going to turn. If you go up the steps, you'll turn right. If you go up the elevator, you'll turn left because they're on opposite sides of the hall. And it's only 2 or 3 doors down. And that's where we're going to be. And we'll do all of the labs on the 28th. We'll meet there at 8 o'clock. It'll be a full day. It'll take us pretty much all the way until 4, 4:30, 5 o'clock, depending. We'll break for lunch, but we'll try and keep the lunch short if possible. So I'd recommend that you guys bring a lunch. That would be the best. There is the city of Moorfield is just down the road a little bit, maybe 5 minutes down the road. So you can run down and get something, but if you can bring something, that's even better. There is a little cafeteria area there, not that they're serving food, but a place to eat. That's kind of nice at the college. And of course, it will be there Thursday and Friday. So other classes will probably be in session. So try not to scream and yell and play loud rock music or whatever while we're doing this. We need to be good citizens. Hopefully the building will be open coming in. I think Isaiah had said that he would open the building for us if it wasn't. So, and Isaiah, did you remember the room number? Was that 205? I hesitate to say.
I think it's 204, but it could be also 205. Yeah.
All right. Yeah, it's not that huge. I mean, it's hard to get lost at Eastern because there's only one building there.
Best way I can describe it is when you get upstairs, go right, and it's the last classroom on your left, I think.
Not the last. No, it's only halfway down the hallway.
Maybe I'm thinking further down.
Yeah. And of course, yeah. So anyway, you'll see.
You'll find it.
Yeah, no problem. And we'll do the labs all day on Thursday, and then on Friday we'll get together. We'll do a review, and then in Friday afternoon we'll take the examination. And as soon as you're done, you can leave. You have 2 hours on the exam. The exam is 75 multiple choice questions. It is not open book. It's closed book. So I find that easy. Yeah, Josh.
I had Wednesday, Thursday as our days. Is that?
Yeah, Wednesday, Thursday. Did I say something different there?
Thursday, Friday. I think
You said Thursday, Friday, yeah.
Oh, yeah. Yeah, I'm showing Wednesday, Thursday. Yeah, 28th, 29th.
All right.
28th, 29th. Yeah, okay. The more I talk, the more I'll confuse everybody, right?
You said 8 o'clock for both days, right?
Yeah, 8 o'clock is better. I mean, if you can't get there, get there when you can. But I don't know if you guys are early risers or not, or how long a trip people have. But that's when we're starting. So
I'll try and be there at 7:30 so I can get the door open for you.
Okay, that's great. Yeah,
Can we use calculators?
Yes, you can. You can't use your phone as a calculator. You can use calculators that are connected to the internet. That's always a bad thing. So yeah, I'll provide little cheapy calculators if you don't have one that you like using. And you'll have scratch paper, of course, and I'll provide pencils, pens, whatever else. But really just wear comfortable clothing for the first day. We'll be up and moving around, working on this stuff. So pretty informal, pretty relaxed. I think as far as logistics, any other logistics on the meeting next week? That people have questions about. The grading, typically what'll happen is I'll take the exams back with me. I scan them and then submit them electronically to ETA. And ETA gets them, they'll probably get them the next Monday. And then they process them. So hopefully by the end of the following week, you'll get your results. They'll send the results back to me and then I'll notify you guys by email. And then it'll be a matter of in a couple of weeks or whatever, you'll get something in the mail that you'll get a certificate, you can put up on the wall that you're certified. You'll get wallet cards that if you're on the job and you need to show that you have your certification, you'll have those. You'll be a member of ETA, so you'll get their newsletter, the magazine, and I think they just send you some other information about how to renew and what your continuing education requirements and things like that. So, so then you will be fully fledged certified because every one of you guys is gonna pass. So, if you don't pass for whatever reason, you have the opportunity to retake it one time for free. So, but you've got to wait 30 days to retake the exam. So what I'd suggest is we've got another class coming up. It begins March 1st. I think it will be face-to-face in April. So there'll be an opportunity to come in on that day to retake the exam in April. So that'll work out fine. But hopefully just do some studying. This is an entry-level thing, so it's not designed to be rocket science. Yeah, Brian?
So in your experience for this class, what do you find is that most students find the most difficult?
Yeah, the math. The math is the one that everybody gets a little bit concerned about. When you're talking about, you will get a question about how do you size a solar array? How do you size a battery bank? How do you do string calculations? Like what's the maximum and what's the minimum in a string? Just like the review questions in chapter 7. So those seem to be the ones that trip folks up. There aren't that many of them. There are only 7, maybe 7 or 8 math questions, and you can miss 18 questions and still pass. So some of the things that really surprise me that people seem to miss are the ones I consider super simple. And I just wonder if they're just not paying attention. I've seen people miss the question about the study of converting light to electricity is known as, photovoltaics, and they miss that. I mean, it's like, really? How'd you miss that? One thing that trips up people a lot is what is energy, basically. When we talk about the difference between watts, watt hours, watts per hour, or kilowatts or kilowatt hours, they miss that. You consume power. Power is in watts, and energy is power over time. So it's watt hours. You buy electricity in watt hours. It's just that you buy them in units of 1,000 because a watt hour is pretty small. So you buy kilowatt hours from the utility, but you're really buying watt hours. It's just that they're measuring them in groups of 1,000. So that's one that people miss all the time. And I try and another area that we'll emphasize has to do with how you size an inverter. For a standalone system, you size it based on the maximum power draw of the system. And for a grid-tied system, you base it on the array size. So I know we touched on this before. Let me find my here's my whiteboard pen. But it's worth repeating because not only for the test, but also because it's important if you're going to size a system. So I'm going to share the whiteboard. All right. Can you guys see the whiteboard here? Yep.
Yeah.
All right. So if I want to size an inverter on a grid tied system, so here's my array over here. So once again, we're going to walk through all of the components in a grid tied, and I'll just make sure I mark this as grid tied. The first thing you come to is what?
Array.
Well, this is the array, yeah. So from the array, we go to what piece of equipment?
A combiner box.
Yeah, it could be a combiner box or it could be a junction box, depending on whether we're combining them or not. Often in today's marketplace, inverters have the ability to accept multiple strings. So often you use a junction box now instead of a single combiner box, because that way you can get maximum power point tracking, keep the strings independently controlled. So you get better output. So in the past, if we had like say 4 strings coming in here, you might just combine them in a combiner box and only have one set of wires. The wires would have to be bigger because the amps are higher. But oftentimes now your inverter might be able to accept 4 strings. So at that point, we're going to come in to the DC disconnect, which is part of the inverter. Usually I'll just make it all as a single unit. This is very common in today's world, where you're just running multiple pairs of strings down. That way, each of these strings is controlled independently of the other strings. So that if there's shade on one, it doesn't affect the whole array, that kind of thing. So that's where the MPPT, you remember the maximum power point tracking device?
Mm-hmm.
This inverter might have 4 tracking devices. So it breaks the array into 4. Which just gets you a little bit better output. All right, so from the inverter, we go to what?
Another disconnect?
Yeah, the AC disconnect, right? And what's the rule with the AC disconnect in a grid-tied system? Where does it have to be located?
Within 10 feet of the utilities meter.
Yeah, basically the demarcation point between the utility and you. So that's 10 feet, within 10 feet of the meter. It also needs to be labeled as the system disconnect, and it needs to be externally operable. So basically you don't want the firefighter or the utility to have to come and open up the box. So you want a lever, something to turn it off at, externally. The other provision is it's got to be able to be locked. They usually have a little tab on there where you can put a padlock, but they don't have to have a padlock. They just have to have the ability to be locked, but they don't have to be locked, which is weird, but there you go. All right. So from the AC disconnect, then we're going to go into your service panel, right? So here's your service panel. And then this goes out to the meter. And like we said, the distance between this and this is less than 10 feet. So these are both outside. This is usually inside. You remember with the service panel, then this is going to go out to the telephone pole to your transformer up there. With your service panel, you remember the 120% rule. So we could come in here if the bus bar rating or the rating of the box is, let's say the rating is 200 amps. And you've got 200 amp service coming in from the utility. You can go to 120%. So I could come in with a 40 amp breaker from my array. Is that clear to everybody?
Yes.
So what size inverter output would that be for a 40 amp circuit? Well, I would take 240 volts times 40 amps. And I get, somebody do the math, 960 or 9,600, is that right?
Yes.
Yeah.
All right, but I can't use all of that because I've got to have put in my 1.25 safety margin that the NEC requires on all wire. So I take that 9,600 and divide it by 1.25. And now what do I end up at?
7,680.
7,680. And that's one reason why a lot of inverters out there are 7.6 kW. Because it's a unit that fits nicely with a 200 watt panel with a 200 watt service. So the other most common you're going to run into is a 3.8 kW. That would be a 100 amp panel with 100 amp service. So all of that just keeps you within the 120% rule. All right, so that's sort of some of the issues there. Well, how did we size this inverter? What size inverter do I need? Well, I already know I can't go more than, with this scenario, more than a 7.6 kW. But do I need a 7.6? I don't know. Well, all of the power that's coming, that's being used, everything that's generated from the array pushes through that inverter, goes to the load. Now, if the loads don't need it, the excess power goes up here and goes to the grid. So that's part of the net metering thing. So if I'm generating too much power, the power I need goes to my loads, the excess goes up to the grid. If I have more loads than what I'm generating, then all of the power I'm generating goes to loads, but more power comes in and goes to loads from the grid. So the amount of power flowing through the inverter in a grid-tied system is independent of the load demand, right? Because if I have too much, well, all the power is still going through there. It's just going to go up to the grid. Or if I have too little power, well, then all the power that's going through goes to the load, but then I supplement it with power from the grid. So the inverter is disconnected from load demand in a grid-tied system. It is connected to the array. 100% of the power that's being generated by the inverter or by the array goes through the inverter in a grid-tied system. Is everyone clear on that? Okay, so I need to size my inverter based on the size of the array, not based on anything to do with load. It doesn't have to be the exact same size. If I have a 5 kW array, I don't have to have a 5 kW inverter, but I need something in relationship with the array. And in today's market, we usually have about a 1.2 to 1.3 inverter load ratio. The inverter load ratio. And we refer, that has to do with clipping. So hopefully that's not a new term to everybody, but so clipping. So I'll demonstrate clipping in a bit, but I want to finish this. All right, so I might have a 4 kW inverter, and that's fine. Usually you're going to have a bigger array than inverter. And that just has to do with economics because the price of panels is cheaper than the price of inverters. So may as well go with a bigger array. There is a limitation, right? And the inverter will tell you what the limitation is. It'll say the maximum array, like this 4 kW might say the maximum array I can hook up to is 7 kW. So I couldn't go bigger than that. So the relationship in a grid tied is between the array and the inverter. All right. See if I can get down here and get a new. All right. So what is clipping? Well, clipping is best described is I'll do it with the single microinverter and single panel because it's just easier to conceive of. But the same thing applies if you're doing a big array with a string inverter. So if I've got an inverter, and let's say I've got I'm using a Enphase M250. Well, the M250, the maximum it could produce is 240 volts. Or no, sorry, 240 watts. They call it a 250 because this is the continuous operation. The maximum is 250. So they just went with that. All right, so if I have an M250 inverter here, and I'm going to be capping off any production I have at 240 watts. Well, during the day, when the sun comes up, let's say I put a 240 watt panel on here, sun comes up and it starts producing. It gets up here and at solar noon, it's producing 240 watts. And then as the sun goes down, it goes off like that. So assuming I have a 240 watt panel and assuming we're under ideal standard test conditions, this is what we're doing. And we produced 100% of the power that we've been able to produce it. So what happens if I decide instead of a 240 watt panel, I'll just mark that here, I go with a 300 watt panel. Well, then my curve is going to go something like this. Right? Okay. So this is my 300 watt panel. But my inverter is only capable of generating 240 watts. So it's going to clip off that top bit under standard test conditions, which seems like a bad situation. But the reality is all of this excess power in the shoulders here is going to be more than the power that's lost. So even on an ideal standard test condition day, I'm still going to be generating as much or more power with the 300 watt panel than I would with the 240 watt panel. So it's still a good thing, assuming the difference in price between these two panels is not too excessive. But the reality is this is under STC, and STC conditions don't happen all that often, right? STC conditions are kind of rare, maybe let's say a dozen days out of the year. So most of the days, if I've got a 200 watt panel or a 240 watt panel and a 240 watt inverter, if this is my 240 watt inverter, my M250, most days my curve is going to look something like this, or it might even look like as clouds come in and out, you know, you get a jagged line. So I would say 90% of the time, the production curve is going to be well below the cutoff mark. So if I go with a 300 watt panel, well, it's still not producing all it's going to produce, but it's doing better, and you're getting a lot more production with the bigger panel. So that's why we clip things. You just get a lot more power because you're going with a larger panel than the inverter's capability. Clear as mud?
So just to be clear, the inverter doesn't stop power production when you're clipping. It's not living up to the full potential of the panel at that moment. Right?
Correct.
Okay.
It'll
All right.
go up to 240 and then it doesn't generate any more than that.
Okay, gotcha.
But it doesn't like blow a circuit or anything.
Okay.
It'll produce the 240. You can exceed its capacity, and that's why you have a limitation.
Right.
Because if all of a sudden I put a 500 watt panel on there, I might blow the inverter. You know, but it has an operating tolerance range, and it'll usually tell you what that range is. Well, it will always tell you. All right, so then let's look at the standalone system. Standalone, we've got, again, the component pieces. We start with the array. Now, what's the next piece? Standalone?
Combiner box.
Be the box again.
Combiner or junction box, right?
Yep.
Depends on how we're configuring it. So I'm going to go in, let's just say we're going to a combiner box. And then from here, where do we go?
Disconnect.
DC disconnect.
DC.
Yeah, DC disconnect. From the DC disconnect.
Inverter.
Inverter.
No, this is standalone.
Oh, 12 volt to 12 volt.
Charge controller.
Yeah, charge controller.
Charge controller.
From the charge controller.
Inverter.
Not yet. What's it controlling the charge to?
Batteries.
Batteries, right? So now I need my batteries. Then from the battery, we go to,
Disconnect.
yeah, DC disconnect, which is probably built in to the inverter. See, I didn't even let you guys say it after wanting to say it the time. So now we go to our inverter, and from the inverter,
To the panel.
yeah, to the service panel. We don't necessarily need an AC disconnect because there's no meter. We don't have to be outside for the utility or the first responders. Typically, you'll want to be, because if a first responder shows up and you don't have a way for them to turn off your system, they'll probably just let the house burn down, you know, if it's on fire, and they'll just go, hey, you know, I'm not putting myself at risk. So you might want a disconnect out there, but that's up to you. All right. So this is the way the system goes. And then from here, you're going to loads. So how does the power flow? Well, 100% of the power here flows from the array into the battery. And that's where it could stop. Let's say you don't have any loads. Well, it's just charging the battery. So what happens when the battery is full? What happens to the power?
The charge controller takes it down to trickle, right? Trickle charge.
Yeah, it'll control that. Or I could have like a load dump.
Hot water heater.
Yeah, water
Yeah.
heater or whatever. So this would be a load dump. And I could take the excess capacity if I've got it and just heat water. All that is just not wasting potential power, you know, doing something with it. So that's part of the system. Well, then let's say I turn on some lights, turn on some loads. Well, what happens? It draws it from the battery through the inverter to the load. Right? What happens when I keep adding loads, keep adding loads, keep adding loads? Well, it just keeps draining down the battery faster and faster. If I'm using loads faster than I'm recharging the battery, eventually that battery is going to go dead. You know, that's kind of where we're at. But this system really could be considered two separate systems. I could have a system without any loads and it would work. Of course, there'd be no purpose to it. And I could have this part of the system without an array, but then it would just drain down and be dead. And that would be the end of it. So we try and size the array based on the average loads that we use in a day just to keep everything in balance. But they're not dependent upon each other. So what power flows through the inverter is based on the loads. And it's based on the maximum power draw. Right? So if I keep adding loads and adding loads and adding loads, well, let's say that I've got a 4 kW inverter here, standalone, and all of a sudden I'm drawing 3 kW. Well, everything's fine. Then if I exceed 4, maybe I go up to 5 kW, this thing's gonna just turn off, disconnect. It's like blowing a breaker. So it'll squeal and it'll say, hey, I don't have any more juice. You know, you've exceeded my limitation. Usually the good ones will just have a breaker in there and the breaker will reset after you turn off some loads. But the inverter size is based on the maximum power draw. So if I've done my work and I've found that I've got 5 kW maximum potential draw, I better have at minimum a 5 kW inverter. I could have a bigger one. I could have a 6 or a 6.5 kW, and that would be better because you're not taxing your inverter to its maximum. But at minimum, it's got to match the maximum power draw. Now, what's the relationship between the array and the inverter? There's none at all. I don't even need to have an inverter. You know, it could be a total DC system. You know, all I care about in this case is the array is based on trying to size it in a way that I replace my daily load every day. And only that's just so that my battery is not draining down over time, or I'm not producing too much that it's wasted. So, but there is, the inverter is sized based on the maximum power draw.
Hey,
Is
Jay,
that all? Yeah.
it's Ted.
Yeah.
So I have a standalone system, and I have the Solark 12 kW as the installer sized it. But between there is a combine. I have two strings, one combiner box, and it all goes directly to the inverter, which has apparently integrated the DC disconnect, a charge controller. It does have a reading that seems to give me a battery reading. So I guess some sort of integrated with the battery management system.
Yeah.
And so I guess in your generic diagram here, some of those things look like it's already integrated into one box,
Yeah.
the Solark.
And that's not that unusual. In your system, what you're going to end up with is you're going to have an array, you're going to have a combiner box or a junction box, and then that's probably just going to go right into the Solark. And in here, there's going to be a DC disconnect. In here, there's also going to be, as you say, a battery management. I should just say a BMS, battery management system, because you've got a lithium ion battery. Is that right?
Yeah.
Yeah. So lithium ion batteries require that there be a battery management system. And then there's also going to be the inverter. And then probably also built into it is an AC disconnect. You know, a way to turn it off here and a way to turn it off over there. Is that right?
Yes, because power's leaving the inverter as AC, obviously.
Yeah.
Into the service panel.
So there's like another switch, isn't there? I think there's one on each side or something.
I think so.
Yeah. And then you could put an AC disconnect here. And then you could go straight into your service panel. Well, I have it here, but you probably just come in as the main.
Yes.
Is that kind of how your system is, and you have this or not?
I don't have a separate AC disconnect. It appears to be all integrated. Integrated with the inverter. My AC disconnect is practically speaking just disconnecting at the service panel, just disconnecting the main.
Okay, yeah, that'll work. But now you don't have any external way of turning it off unless you've mounted all of this outside on the wall.
Correct, and it's inside, of course, and the batteries are just below literally just physically just below the inverter.
Yeah, and so, and then do you have a channel or something that just all the wires go there, or does it connect up?
All the 6 batteries are all. It looks like the 6 batteries. I can't decipher the wiring. They're all 4-aught wires. They're cables. It looks like there's 2. I guess it's a 48-volt system, but they're 2 strings of 3 batteries each is what it looks like, because there's 2 separate external connections that connect into the inverter.
Okay. Yeah, and that's pretty common. Sometimes what they want you to do, and I don't know if this system has it probably do. There's a thing they often will call the rapid shutdown disconnect, RSD. And it's basically a DC disconnect that is
Yes.
now connected to the batteries,
Mhm.
and it goes outside typically where rapid shutdown disconnect. For
When I
grid-tied
when I
systems-
open the inverter, the panel that I guess the user can do, there is I can disconnect the DC load. That's my DC disconnect.
Oh, okay.
I
there's
don't know about.
Yeah, because well, what you run into with a battery system is, if I go back here to the grid tied, well, that's kind of a
Mhm.
mess. The issue is, let me if we have a grid tied system and we're going to our junction box, then we're going to our inverter. Well, let's say we've got an AC disconnect, an AC system. So this is, if I do like an N-phase system, this is a combiner box, comes
Mhm.
through there, and you can combine multiple branch circuits in there. And then from this, you go to a system controller, or what we would call a smart switch. This is kind of the brains of the operation. And then from the smart switch, we would go to our main service panel. That goes out to the meter, then that goes to the utility. And then you would have like a critical load
Mhm.
service panel. And then you can also hook in batteries. And they
Backup.
get connected in here. And then you also, from here, have a I left this. Usually here is where you go to your AC disconnect from there to shut off your array.
Mhm.
But from here, we would go out to our rapid shutdown disconnect, RSD. Okay, the reason for this is, let's say that you're operating as per normal, and you go ahead and shut off. The first responder comes to your house or whatever. Your house is on fire, and they want all of the power to be off in the building before they enter. So the first thing they do typically is they come and they pull the meter. Although that's changing, because now the code says you've got to have a disconnect here at your meter. Have you seen these meter boxes that have like a main disconnect and a few breaker spots out there underneath the meter? If you haven't already seen that, they're coming. It's based in the 2023 code. You got to have it. So your main disconnect's there. So they're going to come and they're going to turn off this main disconnect. That now removes you from the grid. You're now isolated from the grid. So they don't have to physically pull the meter. They just flip a breaker. So that's nice. Now you don't have any power. So what happens? Well, you've got battery backup. So your smart switch says, all right, we no longer have the grid. So I'm going to disconnect here and I'm going to route everything to the critical load panel. I could do a whole house backup, but for this example, I'm doing critical load. So they pulled the meter essentially, but you still have power in the house. The power is running from the array. It's still operating in standalone mode. You still have power going to critical loads. So then they say, all right, now I've got to turn off the disconnect here, the AC disconnect. Well, now you don't have power coming from the array, but the system controller has said, oh, I realize, well, now I'm just going to use everything for the battery. So you still have power in going through your system to the critical loads. So then you turn off the rapid shutdown, and now the battery is turned off as well, and all power is off. So these things, if you go to a house and on the outside of the wall, here's your meter. Within 10 feet, here's your AC disconnect. And also within 10 feet, here's your rapid shutdown disconnect. So all three of these need to be co-located right there, and they just go boom, 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 turning them off. And your disconnect's probably right there. Does that make sense?
Mhm.
Why would you need an AC disconnect when there's one under your meter?
From the array. Microinverters send.
Oh, gotcha.
Yeah, that's all that AC disconnect is for, is to turn off the array. Now, another nice thing about having this meter box here is this is something that's really going to be helpful if you're installing a system. Let's say I've got a rooftop here, and I'm going to put the array up on the roof, and I'm using microinverters. And here's the side of the building. You're going to see how bad my art is now. All right, so this let's say on the west side of the building here, this is the south. This is all facing south here. So over here on the west, this is where our meter is. And it's got that disconnect box right underneath of it. And I want to run my microinverters. Well, I could just run the cord, you know, come down the side of the building here, and I'm going to go to my end phase combiner box. I could have a junction box. Usually you'll have your junction box right there to transition, and you could come through the attic and pop out. But in this case, I don't want to even go into the house. So I'm just going to run down the side here. And from the combiner box, now I'm going to go to my AC disconnect. And from my AC disconnect, I'm just going to hook into this spare double pole breaker out here at that meter. And I've now hooked up my whole system, and I never had to set foot inside the house, which is really sweet. So that saves a lot of money. Saves a lot of hassle too, because some people's houses you just as soon not go into. But yeah, it's and you can use the Wi-Fi. You can connect out here to the Wi-Fi for your combiner box. That's how the communication system works. And oftentimes the big issue that you're going to run into is there's no space in the breaker box. You know, you get an old house or an old system there, and that breaker box is chock-a-block full. And in order to put in a solar array, you're going to have to replace the breaker box. Well, that's usually a $2,500 project to replace that box. And you got to call in an electrician, and you got to do all of that stuff. So if you've got that little disconnect out at the meter, not an issue.
So Jay, if that same scenario had a battery backup, you just similar to your previous drawing. Now you put your RSD right along the same wall with your AC disconnect and your meter disconnect.
Yes, exactly,
Okay.
exactly. Yeah, in ours, we put the switch, the smart switch, the combiner box, the load management. We put all that in the basement, just on the other side of the wall from where the meter is, and then we just ran outside and put the AC disconnect out there, and ran outside and put the rapid shutdown, the DC disconnect, the battery disconnect, maybe an easier way to think about it. And all of that, worked out quite nicely. Now in California, where a lot of this stuff happens, or in more temperate climates, they tend to put everything outdoors. They'll put all the switches, they'll put the batteries, they'll put everything right outside. I would worry about that, because if you're spending $4,000 on a battery and $2,500 on a smart switch and $1,000 on a combiner box, and just sort of have it hanging on the outside wall, somebody sometime is going to figure out there's money there, and they're just going to take it. I would worry about it. So, but now there is a provision in the code for batteries that you got to put the batteries outside, coming up pretty soon. So that's going to be another issue that we have to deal with. But for right now, in West Virginia, you don't have to worry about it for a couple more years. So
Will there be a requirement to move them out
no,
later on? Like if you want to upgrade your system and say, well, now you have to move your batteries out?
maybe. When you say upgrade, yeah, maybe. Well, you're standalone, so you're not even going to tell them. But that's
The lithium ion batteries, does it apply to that too?
Yeah, that's the main thing that they're worried about. They're concerned about thermal runaway in lithium ion. So they're concerned that it's going to catch fire. It doesn't make any sense, because lithium ion are actually much more stable than lead acid. But somebody somewhere got a bright idea that we should put them all outdoors, and they got it put into the code. So hopefully by the time it becomes an issue, they'll reverse themselves. But it's still hanging out there as a possibility. So any other questions? I hit a lot of the high points there, but yeah, Brian.
Well, I was watching your drawing, and the last one especially, you put like a junction box, and then it came down to a combiner box. What's the main difference between the two?
Yeah, with the Enphase system, it's very common that you're going to be up on your roof, or you're going to be on a ground mounted system, and there's specialized cable that connects to the microinverters, and you want to transition that cable to something cheaper, to a regular type, THHN type cable. So you have just a junction box. It could just be something with bus bars in it, very simple. Doesn't need to have any overcurrent protection or anything, but you're just moving from one expensive wire to a cheaper wire there. And then it runs in conduit. But the Enphase requires that you have a combiner box now, because the combiner box not only takes branch circuits and hooks them up in parallel, and the branch circuits, you can only have like 13 microinverters on each circuit. So if you've got more than 13 panels, you're going to need to combine those. And you do that in the combiner box. There are circuit breakers in there, and you just hook them into the circuit breaker. Because again, this is all AC wire. But then the communication system is also built into that combiner box. So it's a unit that they sell that they think makes everything easier. But it used to. Now it's kind of making things expensive and complicated. But it also has things in there like, the communication system. It has the wireless communication system that communicates between the switch, the smart switch, and the batteries. because all of these things have to communicate with each other when you're dealing with load management and turning things on, turning things off. They have to communicate, and they do that wirelessly. And that's
With
in
the combiner box.
yeah. And then
Okay.
there's also current transformers, CTs, that measure how much the array is producing. And it's also where the CTs that measure how much your home is consuming get hooked in. So there's a lot of data stuff going on in that box. So they just
Mm.
said, let's do it all in one box. And that has to happen.
And that's why that thing could cost as much as $1,000 when a junction box is just kind of like a junction box. I always thought of was like in the ceiling when you're just going, you want like maybe three, like an intersection going on.
Yeah, exactly.
Okay.
So the junction box on up there at the array is just that. It can just be a PVC box with a bus bar in it where you're just going for, or it could be just a box with wire nuts. You know, you could wire the things together and transition here's, you know, hot line 1, line 2, neutral, and equipment ground. And so you've got 4 wire nuts and 4 wires coming in, 4 wires going out. Just a place to make that. It's not very elegant solution, and they make better ones. But the combiner box for Enphase has a lot of stuff going on. You know, so it's something that you gotta kind of buy. It also has now a cellular modem built into it as well. So that if your Wi-Fi goes down, it will call in over the cell service. And this can be a big deal out there in rural America, where you may not have Wi-Fi, but you might have cellular service, for example. Let's say you've got it out on a barn, you're installing it on a barn, and you don't want to run your Wi-Fi out to the barn because there's no purpose for that. But it's, you know, you have to get repeaters and all this other nonsense to try and get Wi-Fi out there so it can communicate. But you can just stick that cell modem on there, and if you've got cellular service, it's going to communicate through the cell modem. So So that's all built into the unit as well. So, but it's pricey.
Jay, that little cellular component, is that something that your cellular service will add to your bill? Because it's like
No.
another cell phone?
Yeah, it is another cell phone, but it's pricey because basically when you put that unit in there, I think it's like a 5-year, it may be longer, but it's basically a self-contained service. So it's something you're never going to see. I guess it goes through Enphase, but it's a cellular contract that Enphase has set up. So you pay for it up front in the cost of the little piece of electronics. So it's not a contract you have to sign. Does that make sense?
Sort of.
Sort of, yeah. Well, I'm going to find out for sure because I just bought a couple of things on eBay. I bought a couple of combiners. I don't quite know if they work yet or not, but one of the reasons I bought them is because these combiner boxes cost like $700 if you buy them new. And the communication, the cell modem thing costs like $350 or $400 if you buy it new. So together they're $900, $1,000. I got one for $200 on eBay, and it came with the cell modem. So I'm gonna try the cell modem and hook it into my system, and just see what's involved. My guess is I assume if it's through Enphase, it's fully transferable.
Does it show up as an app on your own cell phone through your own cell phone service, or?
No, it would come through the Enphase monitoring system.
Oh, okay. Which you're
Yeah.
already connected to.
Yeah, that's already an app on my phone. So it
Okay.
would just show up as another communications port. Just like a modem, you know.
Okay.
And they want to require that anyway, even if you have a modem, because they say, well, if the power goes out, your modem's no longer working. You should be able to hook in through the cell so that you can at least monitor it, and we can come in and do troubleshooting if the power is out. So there's a certain logic to it, but it's a logic based on the fact that they're not paying for it. You know, that's they're fine spending other people's money. You know, everybody's happy doing that. So they just say, yeah, Dad's $400. Who cares? You know, it's
At
like,
the risk, my solar system off grid standalone came with a wireless feature, wireless module. And I intentionally did not connect it because I didn't want the monitoring. And
yeah,
so I'm living with the current software that I have and and you know, I don't know how long that life is going to last, but if I end up having problems and they have to upgrade it, I have to reconnect with it.
yeah. Well, and speaking of the Solark, that's the system that we're going to be installing. And I want to just remember to invite you guys to participate in the build. And you can mark your dates. It's going to be May 4th and 5th. So that's a Saturday and a Sunday. I'm hoping we'll get it all done on Saturday, but it's at Eastern. And we're going to be installing a solar pavilion, a solar canopy, a ground mounted system that includes a Solark inverter system and battery backup. So it'll be a standalone system that's installed there at the college. So if you want some, you know, real hands-on, here's how you build a standalone system. You all are invited to participate. And Ted, you've got expertise, but are you near Moorfield or are you coming in?
I'm very near Moorfield. Yes,
Okay.
a mountain range away.
All right. Well, that could be 10 miles or 100 miles, depending on the roads, huh? So,
Absolutely right.
Jay, when it comes to the certification test, are we gonna are we gonna be using like PV watts and like third party stuff like that, or is it like
no,
is
it's all paper and pencil.
okay?
Yeah. Yeah. You may be asked what is PV watts, but you're not going to have to log in.
Okay, gotcha.
Yeah.
And is it all multiple choice, or are we doing like short answer stuff too, or
It's all multiple choice, 75 multiple choice,
okay.
four answers. So you've got basically 25% guaranteed if you just randomly
Yeah,
select. So,
yeah.
so you're all set, you know? So I will say that out of the hundreds and hundreds, I've probably done 500 exams for people. I've only had 2 people get 100% correct. And I've had, a dozen maybe miss 1. Had a lot of people miss 2 or 3, 3 or 4. It feels like the average is missing 10. That just sort of seems to be the average, and I don't quite understand why they're missing the 10, but that's, I guess it's because I just know the stuff. So I look at it and go, well, that's easy. Why did you miss it? So, but yeah, anyway, so yeah, and if you do fail, normally it's because it's failing by 1, failing maximum 2. It's always very frustrating when I've had people who have failed by 1 and they left 1 or 2 questions blank, so you're like, really? Who knows? So anyway, so when you do hand in the test, I'm going to look it over to make sure that you filled in all the answers. And a lot of people think I'm grading it in my brain when I'm looking at it. It's like, no, I don't know where all the bubbles go. I'm just looking to make sure that that you didn't miss something. So that's all. All right. Well, we're up to 2:00. Any last questions before we break?
Appreciate it. Thank you.
Yeah, no problem. And if you do have a question as you're finishing up the studying, just send me an email. It's the easiest way to get a hold of me, and I'll try and get back to you. All right. So I'll see you guys next week.
Thank you.
Take care. Bye-bye.
See ya.